This screencast is going to focus on diffraction. We begin with a bit of a review, and that is, we need to remember that when a beam of light reflects off a surface that has a larger index of refraction, there's going to be a phase reversal. It'll be reflected 180 degrees out of phase. So, for example, if we look at the blue beam of light here, it's traveling through the air. At this point, it strikes the glass, which is a higher index of refraction. It's going to reflect off the glass 180 degrees out of phase. This beam of light here is not striking anything. The two beams intersect right here, and this is where they will interfere with each other, either constructively or destructively. So that means that besides this phase reversal right here, you also have a greater length that the blue beam is traveling than the red beam. And again, red and blue are not their actual colors of the light, but just to distinguish the one ray of light emanating from source S and a different ray of light emanating from source S. So you have two factors you have to keep in mind. Factor one is you're going to have a greater length that one ray travels than the other, which means the crests might arrive on crests and troughs from one wave might arrive on troughs from the other, or you could get crests on troughs or anywhere in between. The second thing that you've got to keep in mind is whether or not you have a phase reversal. And that's going to be true throughout this screencast. Now, you've probably seen this phenomenon before. And these are bubbles. It could be soap bubbles that you're blowing. You have a little plastic container of a soap solution and a little plastic loop, and you blow the soap bubbles. Or it could even be a bit of oil resting on top of a raindrop or a pool of water on a parking lot or a garage or something like that, where that oil is some of the grease in the oil that inevitably gets on surfaces where cars have been. We're going to talk about that in just a minute, about why you get that interesting pattern. But we're going to focus right now in general on section 24.4, interference in thin films. And in order to do that, we're going to have to look at two rules. The first rule reminds us again that you get a 180 degree phase change when you strike a second medium, such as glass or water, that is greater than the initial medium, which is usually air. And number two, the wavelength in that medium, such as glass or water, is going to equal the wavelength in air divided by the index of refraction. Now let's keep in mind that the frequency of the light doesn't change. If it's a red beam of light coming in, it's going to be a red beam of light that's reflected or refracted out. So if you remember that the speed of light equals frequency times wavelength, and if you recognize that the wavelength in the index of refraction is going to get smaller because n is always greater than 1 when we go from air to glass or water or some other medium, that means that the wavelength is going to go down. the wavelength in the index of in the material with a higher index of refraction is going to go down. If the frequency doesn't change, that means the speed of light also has to go down because they're proportional. In other words, the speed of light is going to decrease when it enters the medium of greater density. Now, as we move on to the next paragraph, we need to look at this diagram over here. This diagram has a beam of light starting right there, traveling towards a denser medium, glass, water, something. And at the surface, some of that light is reflected. And of course, we could draw a normal line here, and we would say that the angle of incidence equals the angle of refraction. Now, some of that light that strikes here also continues on and reflects off the bottom of the denser material. It reflects off of this bottom and then is refracted out. And if these two beams are parallel or actually on top of each other, they're going to interfere with each other. And two things we have to notice, those two rules we mentioned earlier. Number one, this beam right here is going to undergo a phase change because it's striking a material with a greater index of refraction. If this is N1 and this is N2, then N2 is greater than N1. And so it's going to be 180 degrees out of phase. It's going to be a phase change of 180 degrees. Now, the beam that manages to continue through the medium and reflects off the bottom of the medium, this part down here, back to n equals 1, because this is not a denser medium down here, that means there's no phase change when it reflects here. It gets a little bit of refracted right there, and it travels out. However, you need to keep in mind that during the time that the light is traveling through this glass or water or whatever it is, it has to travel a longer distance. And that longer distance might be some multiple number of wavelengths of the light. In other words, we can use these two rules and this phenomenon to calculate the thickness of this material that the light is reflecting off of, but also penetrating, then reflecting off the bottom of it. So T is the thickness. So now if we come back over here, imagine then that we have the same kind of thing happening here. A beam of light could be coming, I just erased my nice diagram, so I have to draw that again. There's that. Pick a different color. There's that. It's a little thicker on the side. And if we have a beam of light, we'll make a different color for the beam of light. The beam of light comes there. It's going to be reflected off of there. It's going to undergo a phase change. But some of that light is going to come down here. It's going to have to travel a greater distance. And this is water at the bottom, and it was oil on top of it. These two will interfere with each other. But again, because of the fact that these two, the oil is thicker on the sides than it is at the top, because gravity pulls the oil off to the side, the light is going to be traveling through different thicknesses of the oil, and you're going to therefore get all these different colors. So, have a little trouble here. And now we're ready to look at another phenomenon called Newton's rings. This is what Newton's rings look like. They are the result of light passing through a curved piece of glass in this case. There's the curved piece of glass. And if we imagine a beam of light coming in, refracting a little bit right there, coming to the bottom of the glass and coming out, you'll notice that at this point it's reflecting off a surface where there's air beneath it, and this is the glass right here. And so the index of refraction inside is greater than the index of refraction where the air is, so there is no phase reversal right there. Now, this light that manages to go through the glass and bounce off this material down here, this index of refraction, let's say it's a glass, maybe another kind of glass again. Now, this glass does have a greater index of refraction than air. And so right here, you're going to get a phase reversal. So once again, not only does this beam right here undergo a phase reversal, but it also has to travel a greater distance from there to there, a greater distance than the other beam of light had to travel. And so you're going to get an interference pattern. You can actually calculate the distance, r, the radius, to each one of your dark rings using this equation right there. N would be the order number. So this would be n equals 1, n equals 2, n equals 3, n equals 4 for each of the dark bands or dark rings. I meant m. This is for m. And n, of course, is the index of refraction of the glass. R is going to be your radius. And capital R up here, is the radius of curvature of this lens. So if you measure these particular lengths, the radius, and you know the radius of curvature, and you know which order, 1, 2, 3, 4, etc., the letter M that you're interested in, and you know the index of refraction of your material, you can use this equation to solve for the wavelength of light. If you're using a monochromatic color and you're striking the glass lens with it. In this case, the monochromatic color is red. Now, we're going to come all the way to section 24.6. And this time we're going to have two slits. We'll show you a picture in a minute. And you should remember that if I have a barrier like this, that just has one slit. And if I have some waves of light traveling in this direction towards the slit, and this would be true at the ocean, where they're striking a barrier that has a gap in it for ships to go in and out, that at the other end, it's going to bend as it goes through the opening. That's Huygens' principle. The waves will spread out. So now if we have two slits, or 3, or 4, or 100, or 500, instead of the light going straight through, which of course is what Isaac Newton might have thought, because he thought of light as being particles, he just didn't know much about diffraction. Instead, it does this. If we have two slits, one's there, Each one is going to create these semi-concentric circles emanating from left to right. And they're going to interfere with each other. The crests from these waves will interfere with the crests from these waves, the troughs at the same time. Sometimes it'll be crest on crest, trough on trough, and you're going to get a bright spot if you had a barrier over here and this was photographic film, or maybe it was a wall, you would see bright dots wherever you had constructive interference, and it would be dark wherever you had destructive interference. When you had constructive interference, you would get maxima. We call those places the maxima. And the dark bands, the lack of light, would be where crests cancel out the troughs, and we call those the minima. Now, if you're using monochromatic light, which would be laser light by definition has to be monochromatic. Each of those colors that we see along the wall will be the same color as the laser light. However, if we had a beam of white light, a mixture of all the wavelengths, you would actually get a rainbow. We need a different color for our rainbow. You would actually get a miniature rainbow there, little rainbow, little rainbow, little rainbow. The rainbows would be reversed in terms of red, orange, yellow, green, blue, indigo, violet. And that's pretty spectacular too, if you can get a very, very bright, very, very narrow beam of light that doesn't spread out too much. Now, we're not going to talk too much about Fraunhofer diffraction, but the idea behind Fraunhofer diffraction is that if you put a lens, and there's my lens right down there, if you have a single slit and you put a lens right there to help bend the light, you actually get a brighter band where you're focusing constructive interference, not so wide and bright, not so wide and bright even less. You reverse it on the other side. And that's just an example of Fraunhofer diffraction. And if you were to see it, it would look like this over here. I doubt that would be on the AP. So now we want to get into single slit diffraction. This is kind of what happened when you took your thumbs or two pencils and you put them as close together as you could without them touching, and you looked at some light in the distance, and you could see some black lines in between where you had destructive interference, crests and troughs from wavefronts canceling each other out. And again, we're using Christian Huygens principle that each portion of the slit acts as a source of waves. And imagine I took my compass out and I was making those concentric circles again at every single point. Now keep in mind that A right here, right there, is the width of the slit. Now the width of this slit looks pretty big in the picture. But technically the width of this slit, it would be a fraction of a millimeter. And the idea, again, of course, is that if we do the geometry, if I had a wall out here, for example, this is going straight through, and this beam of light's coming up there. So I'm just looking at this first order. There's my 0th order. Okay? Here's my angle theta. This distance right along here, I could measure. It could be millimeters, centimeters, meters. And this distance I could measure. The distance from the single slit to the wall. That could be centimeters, that could be meters as well. And I can measure this angle theta by using tangent. Tangent would be opposite over adjacent. Once I know what theta is, I can put theta in down here, and I can use this then, assuming I know the width of the slit. I can use it to find the wavelength of the light. And that trig function, sine theta, we talked about the other day in class, when we talked about the longer path that the wave has to travel compared to an adjacent wave. The longer path it has to travel. So we end up with this equation right here, and this is one for destructive interference. The +1 and the -1 mean on either side of your 0th order. So again, if this is your 0 order, you would have destructive interference here and there. We could call this +1 and -1, where the minus sign doesn't mean a value, it just means in the opposite direction. And then you'd get another cancellation, +2 and -2. A, again, is critical. What is the distance between the slits? We'll talk about that in just a minute. In fact, even less than that. So what if we have lots and lots of slits? And this is where Lab 34, which I hope you get to do, comes into play. Because you're going to get a diffraction grating. And that diffraction grating will have hundreds of lines or slits per centimeter. The lines here, we mean little, small scrapes, very fine parallel scrapes in some dark film that allows the light to go through. And the distance between each slit is small enough so it's in the ballpark of the wavelength of light. So we're going to see the diffraction. So this is an important point. A lot of students make mistakes in this area. The letter D is the distance between each slit. However, when you read your diffraction grating, the diffraction grating usually does not give you the value of D. I repeat, does not give you D. Instead, it tells you how many lines or slits per millimeter or centimeter or inch, depending upon the manufacturer of the diffraction grating. So if you have 5,000 lines per centimeter, you need to take the reciprocal of that value to get D, because D is centimeters or millimeters or inches per line or slit. And that's a key point, not only in Lab 34, but you're going to have one of these questions, math problems, on the test over chapters 22 through 24. And when you go to do the lab, again, you're going to be measuring the distance from your diffraction grating. And there's your diffraction grating right there with slits between them. And whereas the distance between the opening for each slit, the distance between each slit is very, very, very small, this distance here, I'm going to call it L. Other books might not call it L, this distance right here. That length could be a meter or maybe 2 meters. It depends upon how far away from the wall you want to put your diffraction grating. Now, the farther away from the wall you put it, the farther apart your dots are going to be. And that means this distance right here can be millimeters or centimeters or even more if you're really far away from the wall. And of course, once again, you can measure this distance and this distance, and that will allow you to find your angle theta. And then once you find your angle theta, you can put your angle theta right in there, because d sine theta is the extra distance that the one wave has to travel in order to interfere constructively or destructively with an adjacent wave. And just for reinforcement, the order number, not like in chemistry where we have the first and second and third order equations, not like in calculus where we have first and second order differential equations. Here, the order number simply means whether you're looking at the 0th order, which is directly across from the diffraction grating, or the ones on either side of it, or the second one on either side of it. And of course, your angle theta gets bigger and bigger as you try to measure it from 0 to the first to 0 to the second. But you'll still be able to use this to calculate the wavelength of light. So if I come back to here, that's your goal in Lab 34, is to calculate the wavelength of the laser light, compare it to the accepted value, and then you can find your percentage error. And we're going to stop right there.